Hello everybody, I hope you guys are doing well today. So let's take a look at this curve and let's ask this question: how do we find the area under a curve? And I think your response probably today on that would be, well, we use the fundamental theorem of calculus. We find the antiderivative, we substitute in our upper and lower bounds, find the difference, and then we have it. But there's an issue with that. And the issue with that is that we can't find the antiderivative of every single function. It's just not possible. And some functions, we could do it, but it's just extremely difficult to do. And what we can do instead, of course, is approximate. Okay? And this brings us way back into the conversation that we had at the very beginning about area. So if I looked at this curve and I said, let's approximate the area under the curve from 0 to 4. Well, our first method that we looked at was using rectangles, right? So let's say I had a rectangle there. Here I'm using the left point, like this. Okay. And that would be one approximation for the area. Or I could use the right-hand point and do the same thing. We also then looked at, well, what about the midpoint? Could we use the midpoint of each interval to make our rectangles? Okay, something kind of like this. I don't know why I redrew that one. And we found out that midpoint was really, really good, wasn't it? The last technique that we used in approximating was to use trapezoids. Okay, which looks something like that, which is also pretty good. Now, if you recall, the midpoint did seem to beat the trapezoid method when it came to the accuracy in reducing the error. However, we left all of that because we decided or determined, figured out, whatever word you want to use, that is if we just use the right-hand point, we can take the limit as the number of rectangles goes to infinity, and that gives us an exact area. And then we saw a connection then between the area and the antiderivative, and we built this fundamental theorem of calculus up, which is terrific. But again, going back to my point here, it's not going to work for every function. And I recall with you guys asking you, okay, we did the rectangles, left, right, midpoint. We did the trapezoids. I recall asking you, is there something else that we could do to better approximate a curve? And could we use something other than lines, right? So shapes, polygons that have line segments for sides. Could we use something that doesn't have line segments to approximate a curve? And I recall a certain student whose initials are IH said, what if we used a parabola? And that's what we're going to look at today is, oh, look at that. Sorry, got an email. We're going to look at that. How could we use parabolas to approximate the curve? Well, let's say we use those same intervals that we're using before on my sketches. And one thing that I want you to recall is that with a parabola, it takes 3 points to make a unique parabola. Okay? So if I split it into these intervals, what I can do is I can make a parabola on this interval using these 3 points. And I can draw a parabola through them. Now, when we think parabola, we think this big U shape, right? But this would actually have to be a really widened out parabola that would look something kind of like that. Okay. Then what we'd do is we'd go to the next interval and we would use these 3 points and make a parabola there. And I hope you're recognizing that, you know, if I draw a parabola through those 3 points, it's going to be awfully close to what the curve actually looks like. And then we continue, right? And then we go to the next interval, and now we use these 3 points, and we draw a parabola through there, and you got to believe that's got to be close, right? And then we go to the last interval, and we use these 3 as our last 3 points, and we draw a parabola through there, okay, to match up. And we think the area underneath those parabolas, whoops, dropped my pen, would be pretty good, okay, a pretty good estimate. We're not going to talk about how good necessarily today, but we know it's got to be good. So let's figure out how we do this. So some things that we have to remind ourselves about. First off, what's the standard form of the quadratic equation? F of x equals ax squared plus bx plus c, if we write it in kind of our standard form there. Now, how about our intervals? Up here I make the note here, we're going to divide into the intervals like we did before, right? We'd say 10 rectangles, or we'd say 12 trapezoids. We're going to divide it into intervals, but this time it always has to be an even number of intervals. And why is that? And sometimes students get thrown off on this because we look at this and we see, well, 3 points, right? 3 points, why does it have to be divisible by 2? Well, notice that this point right here is in both the parabola to the left and the parabola to the right. Same with this one, same with this one. That would be the case if that was true there, and that would be if we kept going to the left as well. And we can see here that we actually have to be divisible by 2 with our interval. So if we take a look at this, my total interval here was going through from 0 to 4, and I used how many intervals? I used 4, and it worked out. If I would have tried to use like 5 intervals, it wouldn't work. If I tried to use 6 would actually work out. And in the way that I kind of think through this is I picture the area under the parabola, and with 3 points, I'm actually kind of creating 2 regions here, aren't I? Now, this is still just in my first interval, okay, but I'm kind of creating 2 regions there. And that's kind of one way that I try to remember that we have to divide it into an even number of intervals. Okay, so we know we have to divide by an even number of intervals. How are we going to set this up? Well, we have to find the area underneath the parabola. We have to find that blue region. Okay, so let's set 3 points here. Now, one thing I want you to keep in mind is I started over here, like this would be x sub 0, this would be x sub 1, this would be x sub 2, and so on. But if I take an area under a curve and I translate it left and right, what happens to that area? And the answer to that would be it doesn't change. So what I'm going to do is I'm actually going to take one of my parabolas and I am going to translate it over. Okay, I'll just draw a parabola maybe that looks like this. Okay, and I'm going to set my 3 points like that so that the middle point, I think that was maybe a little too far, the middle point actually ends up being at 0. All right. Now we're going to call this negative change of x, and we're going to call this positive change of x. So that way we are still counting by the same distances along our x-axis. We're going from negative change of x to positive change of x using these 3 points. I'm going to, now the y values here are going to be important. So I'm going to call this y sub 0. I'm going to call this y sub 1 and this y sub 2. All right, that would correspond with negative change of x being x sub 0, 0 being x sub 1, and positive change of x being x sub 2. Now let's see if we can't find the area under this parabola. So How are we going to do that? Well, remember the equation of this parabola is ax squared plus bx plus c. Now, we don't know what a, b, and c are here. That's okay. We can still find the area under the curve from negative change of x to change of x. So let's write this as the integral from negative change of x to positive change of x of ax squared plus bx plus c dx. So one reason, and maybe you've wondered this, like, well, if we're talking about area approximation, why didn't we do this back when we were doing our rectangles and our trapezoid? And the reason for that is to use this method, which is I haven't said the name, is going to be called Simpson's method. We actually have to use the fundamental theorem of calculus, which came out after we were doing the approximations when we started finding exact values. So how do we find this? Well, what's the antiderivative of ax squared? Well, that would be an x cubed. We'd need a 1/3 in front. 1/3 ax cubed is the antiderivative of ax squared. Plus the antiderivative of bx would be 1/2 bx squared. The antiderivative of c is cx. And we're evaluating this from negative change of x to change of x. Okay, so again, this is why we couldn't do this before. We needed the fundamental theorem of calculus to set this up. All right, so now how do we evaluate our definite integral? Well, let's substitute change of x in. So we have 1/3 a change of x cubed plus 1/2 b change of x squared plus c change of x minus. Now we put the other side in here. Okay, so we're going to have 1/3 a negative change of x cubed plus 1/2 b negative change of x squared plus c times negative change of x. All right, so let's do some simplifying here. There aren't any just x's in here, so I'm going to save myself some parentheses here. I'm just going to write change of x cubed like that. Okay, now what's going to happen here? We have a minus 1/3 a. What happens when I take negative change of x and I cube it? Well, negative change of x cubed is the same as -1 times change of x cubed, which is -1 cubed times change of x cubed. -1 cubed is -1, so this is negative change of x, right? We've done that kind of work before. We did a lot of it kind of in pre-calc understanding, like even in odd functions, what happens when you substitute a negative in. So this actually becomes a negative change of x cubed, and that negative is going to make the negative in front, okay, into a positive. So we have a positive change of x cubed. Now we're going to go to the next one. Now this time we're squaring the negative change of x, and we know when we square it, it's going to become positive. So I'm going to distribute my negative, and this is change of x squared. Now here I'm going to distribute my negative, but here we also have a negative, so that's going to make it a plus, and we have a c change of x. Now, can we simplify this at all? And the answer to that, of course, is yes. How many x cubes do we have? Well, here's a 1/3 a change of x cubed. Here's a 1/3 a change of x cubed. That gives us a 2/3 a change of x cubed. How many change of x squareds? Well, here's a 1/2 b change of x squared. Here's a -1/2 b change of x squared. So those end up canceling out. Okay. C change of x and a c change of x is a plus 2c change of x. Okay. So this is what we get for the area under any parabola from negative change of x to change of x. I'm going to do one more thing quickly with this, is I'm going to factor out a 1/3. That's going to make it a 2a change of x cubed plus 6c. Actually, I'm going to factor out a change of x with that. Okay. I know my video is going to end here in about 10 seconds, and we're going to wrap this up in the next video. There we go.